We are going to finish up the chapter on alkynes with a look at how you could actually synthesize or make an alkyne from a starting alkyl halide. And this will be a good lead-in into our next chapter where we talk about substitution and elimination, because technically this is a type of an elimination reaction. So if we have either a vicinal or a geminal dihalide, those can undergo two successive elimination reactions when we use a strong base. This is often referred to as a double dehydrohalogenation because we lose a hydrogen and a halogen 2 times. That's why it's two successive ones. The terms vicinal and geminal describe the relationship of the halide groups. So if you see the word vicinal, what that means is that the two halides are going to be on adjacent carbons to one another. So for example, if we have two bromo groups, these two bromo groups are said to be in a 1-2 relationship because they're on adjacent carbon atoms. And so that means they're vicinal to one another. Versus geminal, geminal means that you have the groups coming off of the same carbon. So either one of these two relationships where we have two halogens either being vicinal or geminal to one another can lead to having a double dehydrohalogenation when using a strong base. For example, using something like potassium hydroxide, or really any of the strong bases that we just previously talked about, such as sodium amide or an alkyl lithium or a Grignard reagent. Any of those would be strong enough in order to proceed, in order to undergo elimination and produce an alkyne. Starting with a vicinal dihalide, meaning that our two halogens are on adjacent carbons. If we use two equivalents of our strong base, such as potassium hydroxide or sodium hydroxide, we're going to undergo two successive elimination reactions. So when we have an elimination, what first happens is our base wants to attack a proton. So that's kind of the major difference between a base and a nucleophile. Bases like protons, nucleophiles like electrophilic carbon centers. So our base is going to grab this proton here, which is arranged 180 degrees apart from the leaving group. So this is what's referred to as an anti-periplanar arrangement, where there's that dihedral angle of 180 degrees between what's being grabbed and what's being kicked off. So when the base goes and grabs that proton, the electrons will swing over and form a double bond in between this carbon here and this carbon right here. So in between these two carbons where the halogens are on. And then that one carbon would have too many bonds to it, so it boots off a leaving group. In this example, our leaving groups are bromides, but they could be other good leaving groups as well. Chlorides are good leaving groups. Iodo groups are good leaving groups. There are lots of other good leaving groups that we'll talk about later that you haven't even seen yet. So in these examples, we're sticking with halogens. So then when we kick off our bromo group, we would lose essentially bromide ion. We also would have formed water as a side product when the hydroxide grabbed the proton. And what we're left with now is an alkene. So that would represent our first elimination reaction to form a degree of unsaturation. So in this case, we have another equivalent of our base that's going to come in and essentially do the same thing. So notice that this proton and that halogen are anti-periplanar to one another. They're 180 degrees apart, and this is the orientation that it has to be in order for the orbitals to line up, in order to even create the double bond, and then to create the triple bond after. It has to be in that anti-periplanar arrangement. So our base is now going to react again with the proton that's across from the leaving group. It grabs that proton. The electrons will swing over and form a triple bond and then kick off the second halogen. So we lose bromide again and we lose water again. So minus H2O, minus Br minus, those are just what's lost in the reaction as a process of it. And so we end up forming a triple bond in between carbons 1 and 2, because those were the carbons 1 and 2 that our halogens were on. Our vicinal dihalide were between 1 and 2. So in this case, we did form a terminal alkyne. And you also want to count your carbons as well. So we had a total of 1, 2, 3, 4, 5, 6 carbons in our original molecule, and we have 1, 2, 3, 4, 5, 6 in our final alkyne as well. The mechanism for forming an alkyne from a geminal dihalide, where both of the halogens are on the same carbon, is very similar. It just is changed ever so slightly for how they get booted off. So starting off, we still have to have that anti-periplanar arrangement. We still have to have a double dehydrohalogenation. We still have to use 2 equivalents of whatever our strong base is in order to undergo 2 elimination reactions subsequently, one after the other. So starting off, our base is going to grab a proton that is 180 degrees apart from our leaving group. So when these electrons swing over and we form that double bond, the alkene, this is the bromo group that's going to get kicked off due to the orbitals needing to line up and that anti-periplanar arrangement. So that's going to be the first one that gets kicked off in the fast step. So that just means when it says fast, that step is not the rate limiting step. This happens quickly. The second step is slow, and according to kinetics, that would be the rate limiting step that determines the rate of the actual reaction that we see. So then we did one elimination reaction. We formed an alkene, and that's actually how you would synthesize alkenes as well, we'll see, is through elimination reactions. And so with the second equivalent of the base, we're going to remove another proton. Those electrons will swing over and form our triple bond, and we'll kick off our bromide ion. So in each case, we see minus bromide and minus water. We lose those in each elimination step. And so we have the same product here that we had in the last one, a terminal alkyne as well. 1, 2, 3, 4, 5, 6. The triple bond, notice, was still placed between positions 1 and 2, even though we had both of our halogens starting off on position number 1. 2 protons were lost from position number 2. So starting off, we lost a proton from position 2 in the first elimination, and then we lost another proton from position 2 in the second elimination. Technically, if there was not 2 protons there, if you had another group there, you couldn't undergo 2 successive eliminations then. So it's a requirement that you have 2 protons that can be lost as well on that carbon that's next to the geminal dihalide. Otherwise, it wouldn't work because your base wouldn't be able to abstract both of those protons in order to facilitate the elimination reaction. So whether you have a vicinal dihalide or a geminal dihalide, they can undergo 2 elimination reactions, sometimes referred to as double dehydrohalogenation, in order to synthesize alkynes. We're not going to draw the mechanism, but technically this can occur with internal alkynes as well. So we can form an internal alkyne if we have, for example, an internal geminal dihalide. So geminal, they're both on the same carbon. And in this case, the 2 carbons next to our geminal position each have 2 protons available that can be eliminated one at a time, essentially. So you're going to end up with a mixture of products. In this case, we're going to form a triple bond in between this carbon and this carbon. And then in another product, you could also form a triple bond in between this carbon and this carbon. So as long as there's 2 protons on the carbon next to the geminal dihalide, they both can be eliminated with 2 equivalents of a strong base. And they can be grabbed one at a time. So the hydroxide can grab both those protons, and that would lead to our product that we see right here, where the triple bond is in between this carbon and this carbon. Or it could grab this proton and this proton, which would lead to the product you see at the bottom here, where you have the triple bond formed between that carbon and that carbon. So with internal alkynes, recognize that you'll get a mixture as long as 2 hydrogens are available on the adjacent carbon to the geminal dihalide. Lastly, we're just going to go through a review of some of the reactions that we talked about of alkynes and remind you of the reagents and what the final products were. So if we start in the upper kind of right corner here, when we had an alkyne and we reacted it with hydrogen and a catalyst, we ended up with an alkane. That was our hydrogenation reaction that went all the way to an alkane. If we reacted it with potassium permanganate and acid, that was a type of ozonolysis reaction or oxidative cleavage where we broke the alkyne, we cleaved the sigma bond and the pi bond, and we ended up with carboxylic acids. If we reacted our alkyne with borane tetrahydrofuran followed by sodium hydroxide and hydrogen peroxide, we ended up with an aldehyde. So that was equivalent to our anti-Markovnikov oxidation, where the least substituted side of the terminal alkyne was oxidized. If we did a hydration reaction using mercury sulfate as a catalyst and sulfuric acid, we ended up with a methyl ketone because the more substituted side ended up becoming oxidized. So that is kind of the opposite side of the coin of the borane tetrahydrofuran reaction. Either we oxidize the more substituted side and get the methyl ketone, or we oxidize the least substituted side and get the aldehyde. This says CH3 under that dot right there because the dot's showing you where this is at in the original alkyne. If we used a strong organic base, such as sodium amide, alkylithium, or a Grignard reagent, we formed an acetylide ion when we deprotonated the terminal proton, the acidic proton there. And then our acetylide ion could be further reacted with a variety of things. We could react it with an alkyl halide to give us an internal alkyne. And that could change identity depending upon the alkyl halide used. Or we could use ketones, aldehydes, or formaldehyde, and get a variety of alkynes mixed with alcohols. So we ended up with either primary, secondary, or tertiary alcohols, depending upon if we used a ketone, an aldehyde, or formaldehyde. So those were all things that we could do with that acetylide anion. If we used an alkali metal such as lithium or sodium in liquid ammonia, we saw that metal dissolving reduction where we ended up with trans, or in other words, E-alkenes. If we used HX, where X is some halogen, we could end up with one of two things, depending upon if we had one equivalent or two equivalents. This is specifically showing what you would get with two equivalents right here because we're ending up with a dihalide, a dialkyl halide here, where you have the two halogen groups added to the more substituted side here. If you had only used one equivalent of your HX, so HBr for example, you would have ended up with an alkene, and you would have had the halogen added to the more substituted side. You also could have a halogenation reaction where we have excess or we have one equivalent used, so same kind of idea here, only for example you'd be using Br2 or Cl2. If you have excess, you're going to end up with 4 halogens added, two on the more substituted side, 2 on the least substituted side, so you get a tetrahalogenated product. If you only use one Aq, you're going to get an alkene, and you're going to have a halogen added to each side of the double bond. If we use a poisoned catalyst with hydrogen, such as the Lindlar catalyst, you're going to end up with a cis-alkene or a Z-alkene, where the hydrogens are added to the same side of the double bond, so cis arrangement. And another oxidative cleavage reaction was ozone followed by dimethyl sulfide or H2S, where we got carboxylic acids, same as the potassium permanganate and acid. So we're cleaving the sigma and pi bonds of the alkyne, and we're getting products of oxidation, which they are going to be carboxylic acids.